Alright, in our discussion we've now learned how to draw Moore's circle and find the values of the two principal normal stresses, our sigma A and our sigma B. And at this point we're going to discuss the maximum shear stress and how that fits into the picture. And we're going to start by thinking about this same example that has this arbitrary stress state of sigma x equals 8,000, sigma y equals minus 3,000, and the shear stress of 6,000. And we've drawn this before in our planar view of looking at things because we've dealt with in plane or the simplified stress state. So we have a plus 8,000, a compressive stress in the y direction of 3,000, and a positive shear of 6,000. That's how we've drawn our arbitrary stress states. But if we think about that in terms of our 3D stress state, if we come over to look on page 6-11, we actually have our cube, or our full three-dimensional structure, where if we draw the stress state that we have talked about, you would have our cube that has 8,000, 6,000, nope, 3,000 sigma y compressive, and shear along the face of 6,000. And we do the Moore's circle process, or find the principal stresses, to figure out the point at which the shear stress is 0. If you come back over here and look at Moore's circle, we have found the rotation angle, and in our transformation matrix that's the 23.75 degrees, and on Moore's circle that's the 47.5 degrees. But when we rotate through those points, we end up on the normal stress axis. So the coordinates on this Moore's circle plane for the principal stress really is 10, 6, 4, 0, and 0. The tau is gone. And same with this one. The coordinate pair is minus 5, 6, 4, 0, 0. Tau xy equals 0. That's the point of the coordinate transformation. So if we transform our arbitrary stress state, that in this case is the example here, we do our stress transformation and we find the location at which our sigma A equals 10, 6, 40, and our sigma B equals minus 56, 40 in this example. Things jumping about. So I'll try that again. That sigma A is 10, 6, 40, and sigma B is minus 56, 40. Alright, so all of that is to say that the shear stress are 0 at this orientation when we have found the principal stresses. The stress in the z direction coming out of the plane is also a principal stress. If we find the right orientation so that the shear stress is 0, there is our third sigma c. If you recall back from the very first day of this, we had our multicolored porcupine of the stress state, and there is a sigma c. When we deal with arbitrary stress states that have the simplified version, the plane stress case, where we only have a sigma x, a sigma y, and a tau xy, that means that our sigma c is 0 for any case that is a plane stress case. If we think about this in terms of what the Mohr circle looks like for different possible cases of signs of sigma A and sigma B, if the principal stress values are of opposite sign, as is indicated in this first example, we have a positive sigma A, we have a negative sigma B, and sigma C is always 0. Okay? That's thinking about our little stress state as if we're rotating about sigma C coming out of the page. If instead we think about what the circle, what circle would be circumscribed if instead we rotate about sigma A, how is that going to vary? Well, we know that sigma C is still 0, and sigma B can vary between 0 and its maximum negative value. So sigma B is here, and any or all variations make a smaller circle. Okay? Likewise, if we take the rotation to be about the B axis, and we think about, we know that sigma C for this stress state is 0. We have our positive sigma A, and we end up with this set. So essentially, we have 3 circles. Sigma C is always anchored at the origin, and this thing is known as 3D Mohr's circle. It is looking at the transformation about the principal axes, these principal axes that is the rotation around the sigma A, the sigma B, or the sigma C axes. So what we really care about is the largest possible value of the shear stress for a given stress state. If we come back to the simple planar case that is gone off of the page, that is on this page, if we look at the Mohr circle for our same stress state, the largest value that the shear stress can be is, in fact, in this case, the radius of the circle. So this value here, or this value here, that's the largest positive value for the shear stress. That's in the case of sigma A and sigma B being opposite sides. If instead or in this case, sigma A minus sigma b over 2 gives you that value if sigma A and sigma B are opposite signs. If instead you have sigma A and B are both positive, what would this 3D Morse circle look like? If we have a sigma B and a sigma A, and we know that sigma C for our plane stress is always 0, so we would have the largest possible circle, we would have our sigma B, sigma C, and our sigma A, sigma B. So for this case, the largest possible radius, which is the shear stress max value, is sigma A minus sigma C over 2. Okay. Likewise, if sigma A and sigma B are both negative, we have a sigma B and a sigma A, and still our sigma C is 0. We have our largest possible. We have the sigma A rotation about B. In this case, we see that this radius value has to be sigma C minus sigma B over 2. So this is a little cumbersome, and again, maximum shear stress here, it's always the radius of the largest circle. Depending on the relative signs of the two principal stresses, it's a different pair of principal stresses. What we can do instead is reorder and rename the principal stresses in order. And this is where the sigma 1, 2, 3 scheme comes in. And now Microsoft Word is giving me issues. Hello? Okay. Back with it after a Microsoft Word recovery. So, rewinding just a little bit, if sigma A and sigma B are both negative, we always know that sigma C is 0. We have a different set of 3 circles. But it's always this radius that is the radius of the largest circle is always going to be the maximum shear stress value. In this case, it has to be sigma C minus sigma B over 2. And that's a lot to keep track of. And that can just simply be eliminated if we take our sigma A, sigma B, sigma C, sigma A, sigma B, and sigma C, reorder them in value and rename the principal stresses or refer to them as sigma 1, sigma 2, sigma 3, where sigma 1 is the largest value, sigma 2 and sigma 3 are smaller. So sigma 3 is your most negative, or most negative, depending on the relative signs of the normal stresses that you've got. Then we have this very important definition where our max shear is simply sigma 1 minus sigma 3 over 2. And you don't have to contend with all these different possible cases of your signs of sigma A and sigma B. Doing this transition to refer to them as sigma 1, 2, and 3 lets you always end up with this equation for maximum shear.